I taught a PLC 3 class, and one of the questions on one of my tests, I just threw it up there, and I says, "What does PLC stand for?" You'd be surprised. And these are the people that's already had 2 semesters of PLC. Programmable logic controllers. A lot of people call them programmable controllers for short. Some people call them just PLCs. By the way, this is the O book. If you got the O book, if you bought a used book or something, this book right here should be fine too. I think the extra chapter, they talk about the RS Logic 5000 software, which we can't teach right now. Program Logic Controller Overview. And this is what we're going to do, describe the invention and development history of PLC, discuss the benefits of PLCs over electromechanical relay logic systems, distinguish between fixed and modular PLCs and devices. And I might have to go down when we take a break and bring one of our modular PLCs down here. Discuss the difference between Intel and Motorola microprocessors. I don't know why they want us to do that. Most of our microprocessors, most of our PLCs don't. Have y'all heard Intel? Motorola? Now these are the 2 big guys. Explain the difference between random access memory and the devices in the PLC in the computer. Now what you got to understand is that PLCs are computers. So a lot of the language or the terminology we use in PLCs in computers applies to PLC. Especially when it gets to trying to figure out what type of PLC you need and what features do you want. So it's pretty important that we learn a lot of terms or terminology. Explain the difference of a read-only memory devices. Explain the use of address encoders. List the major components of PLC, of the components of a PLC power supply. I don't remember that in the book, but I can show you that. Describe Allen Bradley program control devices. Now, of course, I think I explained you that there's a lot of people that makes PLCs. Allen Bradley is by far it's made by Rockwell Enterprises, and it's a subdivision of that. Allen Bradley is by far the most widely used PLCs in the United States. But like I said, we've got a unique situation in our area, and that we're getting a lot of German companies moving. The predominant PLC inside in Germany is Siemens, or even in Europe. So we teach this class. This is going to be predominantly Allen Bradley PLC. But what you're going to learn, guys, is that once you learn one, it makes it extremely easy to learn any of them. I didn't say Siemens. I said what? Any of them. Because most of them support the language, programming language that we're going to talk about. So the book is kind of using terms that you don't hear very much. We do have devices. We have what we call, so basically the makeup of a computer. Let's go ahead and look at a basic slide. And you can pick up your phone and you can see most of these devices. So one thing, and they left out a bunch, they got the central processing unit. This would be great. But what good would it be on my phone if I could not dial a number? Right? You understand? So we have to have inputs. We have what we call input ports or input portals, where we bring information from the outside world into the computer. Well, what would happen if I bust my screen all up? Well, you've lost your output, right? You understand? So computers are not any good without inputs and outputs. So input ports are portals. So a portal is an entryway into, right? We use that term a lot. You know, ships been using the term portal for all years, where the ships come into to access a country, right? So we call these things ports. We have input ports and we have output ports. Everybody okay? Now, we have 2 types of portals. PLC, all PLCs that I ever used supports the first one, and that's what we call digital. Now, digital means we deal with either off or on. So that light switch back there is digital. Either can turn the light what? On or off. So that's most of our ports are digital ports. That's all they do. They look for a switch to be open, a sensor to be made, something happen. It either says it's on or what? Off. And then our output ports are usually digital. Most of our output ports are digital. So when I flip that light, this would be an example of an output. I either turn the light what? On. So the input would be the what? The light switch, which is controlling. And then the output would be our light, which is the load. And this is a perfect example of it. Now, for a long time, this was the main thing that PLCs used, because that's what computers love. Computers love digital. There's nothing analog about this. Right? I understand. Even the information we see when we get a phone call, there's only one thing analog that I know, or two. Probably the microphone and the speaker. That's probably where they have to go from analog to digital to digital. But the problem we have is that most things in nature does not vary digitally. So some PLCs is becoming more popular to have what we call analog ports. They call it a variable port. I've never heard it called that. The textbook, I don't know if they've changed it. So the PLCs are guaranteed to have digital ports, and some of them have what? Analog ports. So anything that's has the ability to constantly vary, we say it can vary between 2 points, an infinite number of combinations. So some of y'all might have a light dimmer at your house. Well, that's analog. And what can you do if you got a light dimmer on your house? You can turn it all the way on or all the way off, and you can set it any range in between. Are we okay? But the problem is nature does not vary with some digital is pretty easy to see. You know, you crank your car, you either crank it or you don't crank it, right? You understand? When you turn your headlights on, they're either what? On or off. I don't know of any cars that I do know some cars that when you turn them, your headlights turn. Turn into the headlights would be analog, but what's some advantage? What's some examples of analog that we run into every day? Huh? Well, that would be the temperature, but temperature is analog. So if I wanted to input a temperature, first of all, we'd have to have what we call a sensor. And did we talk a little bit about sensors? What does sensors do for? You remember? What does sensor do for? What does our sensors do? Converts something physical into something electrical, right? So we do have temperature sensors out there. And if they are, we can have digital temperature sensors, which mean they trip at a certain place. So the temperature sensor in your HVA system is digital. So you set a threshold, and if it exceeds it, it either turns something on or turns it off, right? You understand? But the temperature itself is varying what? It's analog, right? Right? Sunlight, is that digital or analog? Yeah, analog. I mean, huh? Yeah, it's definitely analog because, you know, I get up at 7 o'clock in the morning or 6 o'clock and it's kind of dim out there and it gets bright, right? You understand? Then it does what? It starts dimming back down if we don't have any clouds. So it's analog. Pressure can be analog. Levels can be analog. So they figured out that, you know, sometimes we need to have analog inputs. So I think this guy right here has 2 analog inputs on it. And the 1200 right here has 2 analog inputs. They're labeled A right here at the top. So that's built into this PLC. So analog, these guys don't have, this guy has an analog, that guy has an analog output on it, which means it can generate an analog, like to control speeds or control intensity or stuff like that. But you had to get that as an option. It comes with 2 analog ports on it, but the analog output, you have to do that with as an option. So this is kind of like what analog is. So analog can do what? Yeah, it moves around, it could be anything. So technically, but you have to set an upper and a lower limit. It's like, and the upper lower limit don't ever change. It's not like the temperature. When you listen to weather forecasts, they say the high today is going to be and the low today is going to be this. On these guys, your upper and your lower limit never changes. Usually on in industry, or especially on PLC, analog could be from 0 to 10 volts. But where could it be between the 0 and 10 volts? Anyway. I think the Siemens, you can actually tell it that you have 0 to 5 volts, but you have to tell the PLC what limits you have. This guy is from 0 to 10 volts. Digital is either what? On or off. Now the voltage level on digital depends on the input port, what's recognized by the input ports on the PLC. Just about all PLCs, I'm not saying all of them, the predominant number of them use 0 volts for this guy, and it uses 24 volts. And that's pretty standard. If it's DC. So, the 1200 is a DC, DC, DC. So that means it's powered on DC, the inputs are DC, and the outputs are DC. That's what that means. This is an AC-DC relay, which means it runs off AC, the inputs are DC, and the outputs are relay. And we'll talk about the advantage of that and the disadvantage of that too. And it's the nominal voltage on the inputs is either put 0 volts or what? 24 volts. So this is the basic makeup of a computer. Gotta have a what? Gotta have a power supply. What's the function of the power supply? Probably convert AC to digital. Just about all, every PLC that I've ever seen runs off of DC, but they have to have a power supply. The power supply can be internal, which on this one, it's actually internal. It's got an internal power supply. So if I was to come over here and look at it, I would see, they call it DC out. And then they got plus and minus. So here's the actual DC power supply right here. It's inside built into it, right? And then some of them have analog input, some of them don't. They will have what the book is calling discrete, but the PLC don't call it discrete. They call it discrete means they are not there or something like that, right? We don't call them discrete inputs. We call them digital. Are we okay? Makes sense so far. So we have two types of PLCs. We have what we call fixed PLCs. Y'all go ahead. Now this has changed a little bit over time, so we'll talk about what most people are doing now and the way it used to be. This is what we refer to as a fixed PLC. This is a Micrologic 1000. And basically on a fixed PLC, you get what you buy. There's no very few options. So what we have is this says, can y'all read that? And so these are indicators. Here's the actual input connection to our input ports right here. And N0, 1, 2, 3, 4, 5, 6, 7, 8. So this has 9 input ports on it, and they're single inputs, single bit. We'll talk about that next lecture. And then there's 9 of them, right? 0, and you got to learn in computers we start numbering at 0. 0 means something. In the decimal number system, 0 has no weight. But I've seen college football games where the kicker's wearing 0. And the kicker is somebody, right? You understand? So that number is a what? It's an address. Does that make sense? So this number doesn't have any weight, but it's kind of like an address or number. These are our outputs down here. So this is where we make our outputs. 0, 0, 1, 2, 3, 4, 5. So this guy's got 5 outputs. And they're all digital. And that's it. What if you want to expand it? You can't. It's a fixed PLC. This guy here, it runs off of, it's got DC inputs, it's got relay outputs, and it's powered by AC. So here's this right here. It's called, oops, must be down there. Yeah, L1 and L2, or L1 and N. So this would be neutral, and then this would be where we connect. Should connect to ground connection. Okay. Now this guy here runs 120 volt outputs. We'll talk about how we set that up, but this is where we set it up with these jumpers right here. So if you get this PLC, you need to leave this thing, leave this door latch, right? Everybody okay? And you won't get in trouble. And these up here are 24 volts. For our watt, 24 volts. This is a fixed PLC. So fixed PLCs are the cheapest PLCs you'll buy, but you get what you pay for, right? Everybody understand that? That makes sense. So this is what the slide says. The slide says the number of inputs are set, the number of outputs are set. Number of input ports cannot be expanded. The number of output ports cannot be expanded. Are you okay? That makes sense? So these are the cheapest ones you'll buy. So we've got a little unit over there we call a Bosch unit. It's got a little tiny PLC, and it's a fixed PLC. Because it does exactly what we want it to do. It has no reason for expanding, unless we ripped it out of the unit it's going to run in and try to use it somewhere else. Which is like, as long as we didn't exceed the inputs and the outputs and the right power was available, you could do that because these guys are programmable devices. What do we mean by devices that are programmable? Yeah, you can change what it does. Modular PLC, which is what we got over here. This is an Allen Bradley SLC 504. And what you do is you have a power supply. There's a power supply. So it's converting AC into DC, right? And then you have what we call the processor, the central processing unit, which they consider to be the unit, right? In computers, the central processing unit is a little chip, and in PLC, they talk about the actual processor as everything that's inside it. And we'll see that. And then what you do is you buy modules. We can't rip these out, guys, because they're wire tied down. But you buy modules depending on what you want. So this guy right here's got 16 inputs and 16 outputs. But if I wanted to expand it, what could I do? I could add another module. If I wanted to add analog, I could add another module. So this guy's got, it's got 1, 2, 3, 4, 5, 6. It's a 7-slot rack. We call this a rack. It's a 7-slot rack, but one of them is eaten up by your CPU. That means I got 6 modules. I decide what I want. Right? You understand? I can have AC outputs. I can have DC outputs. I can have an AC output right here, and I can have a DC output right there. I can have an AC input right here and a DC output right there. You know, I choose what I want. So the features of a modular PLC is basically you get what you want. On this, if I lose one of my outputs, I'm screwed. If this, I lose one of my outputs, all I might have to do instead of buying the whole PLC, I can do what? Just swap the module out. Just get a new module. I could carry spare modules. If all my PLCs are the same, right, you understand, then I could have a spare module in there. If I burn one of them out, I could be back up and running in almost no time at all. So these guys are easy to troubleshoot, right? You understand? They're very flexible, they're very expandable, and they're very expensive. So if I can buy a fixed PLC to do what I need to do, that's what I'm going to do. Or I'm going to come up here, you know, some people will spend a lot of money because it's a lot of money. We used to teach A+ classes, and which is computer repair. And the student got all involved in it, and he got a computer place that would give him credit. And what did he do? Oh, he bought the best thereof. His wife ended up divorcing him over it. But anyway, so you got people that goes out and buys these cell phones. You know, they got to have an iPhone 8, and all they do is check Facebook on it, their email, right? But they've got an iPhone 8 or whatever they have out there. So you have people out there that want the best, even though they don't want it. Or they go out and buy a Ferrari and they'll never get over 60 miles an hour. So yeah, a lot of people will buy these things just because it's expandable, even though they never expand it. Are we okay? Then we got the newer type of PLCs. These are basically what I call hybrid PLCs. Some people still call these modular PLCs. So the way this guy here works is that we have a power supply. We call this whole thing, what do we call this? A rack. And then what we have is we have something called a backplane. Now the backplane is nothing but a bunch of wires that brings all the information from your CPU down these slots right here. And they're all electrically the same. So it doesn't make it, you can skip over a slot if you wanted to. It's just that part of your program, when you specify the module, you have to specify the slot number. We'll look at how we can address these things later on in our program. We call this back in here is called a backplane. Now, what we're doing on most PLCs now is we're doing away with the backplane. What we do now is, where's my little sequence PLC? Oh, I got it now. What we do now is our PLCs, we buy them, and then they have a certain number of inputs and a certain number of outputs. So it sounds like it's a what? It sounds like it's a fixed PLC. You say, oh, it sounds like a fixed PLC. So this is a 1200. Siemens 1200, or Cymatics. Siemens is the name of the company. They're PLCs. Most of the people call them Siemens, but they're actually Cymatics. This guy right here has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's got 14 inputs. And it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outputs. Right, you understand? And then it's got analog. That's what this right here, it says analog inputs. Y'all can't see it. It's got 2 analog inputs. And then it's got a little place right here. It comes in sealed. I have to show y'all. But they call these signal cards, and you can get anything, almost anything you want to snap it. And this is the one analog output port right here. This didn't come in the PLC, but that was optional. Now what they're starting to do is they're, instead of using a true backplane, they run the backplane through the modules. So if I was to take this off, you would see there's a little old snap in here. And if I snap this off, here's the backplane right here. So what I would do is I could buy another module like we've done here, and I could slide it on there and lock it in. And then I can add whatever I want to. I think this guy takes up to, I think it's 8 cards. But they can be input, they can be output. This side is for communication. This side is for input output. So communication, converting how we communicate with it. So this guy right here uses Ethernet IP, which is very Ethernet, which is one of the standard interfaces that a lot of your PLCs are going to, even though we'll look at different interfaces, how we connect to the PLC. We got to program it, right? You understand that? So we got to have it communicate with it some way. Well, they have different methods that they'll use, and we'll look at this. But this guy uses regular Ethernet, and then this right here is what we call a switch. So what it does is it allows me to hook multiple things together. And that's a communication module, right? Makes sense. And this over on the wall, on the left. And then, but is it a modular PLC or is it a fixed PLC? Kind of both, ain't it? Yeah, it's kind of both, right? I called it a hybrid PLC. They called it modular, but I called it hybrid because you can use it as a what? You can use it as a fixed PLC, or you can upgrade it. You can expand it. And there's a whole list of modules that's available for this thing that can do a lot of analog. We can go to different types of we have different ways we can send information. We can send it by using voltage levels, right? You understand? Or we can send it with using current levels. There's a technique out there called the 4 to 20 milliamp current loop, which is very popular in industry because it's really immune to noise, electromagnetic interference. So, you know, if this thing right here generates a magnetic field, and I've got a piece of wire right up against it, and that magnetic field cuts through that wire, it's going to try to generate a voltage into the wire right beside it. We call it EMI, electromagnetic interference. And you can imagine how much electromagnetic interference you have in a plant. So one of the ways we can connect our inputs and outputs is called the 20 milliamp current loop, 4 to 20 milliamp current loop. And it is really noise immune. So that means it'll handle, voltage levels are real easy to change. So this is what we're running into now. This is what the 1100 uses right there. If you look on the side, it's got a little panel I can knock off, and I can stick more modules onto that thing. So this is what's very, very popular in PLCs now. It's kind of a hybrid. So you can get a real cheap version of it and use it as a fixed PLC, or you can do what? Or you can upgrade it. Most of them now are going to these. These are compact flash cards or memory cards. So you can literally expand the memory on the card instead of tearing it open. You can just stick a card in here and expand the memory. It's becoming very, very popular too. The memory. So this, we call this a DIN rail though. I forgot what it is. This is an industry standard. So I think the 1100 mounts on a DIN rail. Some of our compact logics we have down there, I'll bring down here to show you all those. They mount on DIN rails. And when we go over to the mechatronics lab, and you'll actually see PLCs in action, you'll see those mount on DIN rails too. So it's very, very cool. So that's modular PLCs, and then what we call fixed PLCs, and then what Rich calls hybrid PLCs. So they won't be on the test. What Rich calls the test. So, okay. Now, what does this consist of? Well, it consists of a unit. So, when I first got involved with computers, which I'm not going to tell you how long it was, this was back when we had a version of computers called mini computers. So we had mainframes, we had mini computers. We didn't have any microcomputers out there. And the central processing unit was made up of 3 big old circuit cards because they spread it out between the tasks. The advantage of spreading the function of the microprocessor over multiple units is that it runs extremely high. So y'all know if you've heard of supercomputers. We got 2 supercomputers in the state of Alabama. We got one up at the University of North Alabama, and I think Auburn's got one. And these guys do billions of instructions per second. These guys are screaming. But they're huge. They're very, very expensive. Well, anytime we start trying to make these things smaller, we do one thing, we sacrifice speed. But the smaller we can get them, the cheaper they become, right? You understand? So they went and came up with something called a microprocessor unit, which took everything that was inside a true CPU, not what we use in PLCs. So PLCs, we call this guy the CPU. In computers, we call the CPU the actual central processing unit. We call one of these things a microprocessor because everything that's in a multi-board central processing unit was shrunk down and put into on one silicon wafer. So it's kind of misleading in the terminology. So on a computer, on a PLC, this whole thing we call the CPU. Okay, makes sense. Now, what does it consist of? Well, it consists of a chip called a microprocessor, also called an MPU. It consists of timing circuits. So everything inside the computer is what we call it synchronous transfer, which means everything is timed. We have two ways we can send data. We can send it asynchronously, which would be untimed, or we can send it synchronous, which would be timed. Synchronous is so much faster, but it's a lot more expensive. So most of our communication outside of the computer is asynchronous, like Ethernet. Ethernet is USB, that's asynchronous, because it takes a lot less of conductors and interfacing to do that, right? Does that make sense? So we have to time everything. So there's clocks in there. We'll talk about address decoders. That's not usually inside the processor. Then we have what we call memory. So the basic parts of a computer is we have to have a central processing and we have to have memory. And then we have to have input portals, and we have to have output portals. That makes sense? The address decoder is usually outside of the processor. Now this would be, in the old days, this was the CPU. For PLCs, what they've done is they've adopted this module right here. They call this the CPU. With the PLC, it's okay, but technically in computers, this would not be the CPU. The CPU would be inside this, right? But everything that this says is inside this module. It's one module. So one of the things that when you buy a PLC, you buy it by what they call the CPU. It's going to be a model number, but it's not the model number of the microprocessor. That's very, very hard to find on PLCs. And there's some of y'all have heard the processors AMD puts out. They call them Athlons, Xeons, and all that kind of stuff. Intel calls theirs i5s, i7s, right? You've probably heard of those. But inside the microprocessor, it's real hard to. I haven't been able to find anybody that tells you the actual microprocessor that's inside. So in microprocessors, they call this whole guy right here the CPU. Not microprocessors and PLCs. Okay? Makes sense? So terminology kind of moves between trays. So what does a microprocessor do? This guy says it's the brains of the computer. This guy, in my opinion, is not the brains. All this guy does is fetch and execute instructions. That's all it does. What's the brains of a computer? What can a microprocessor do? A microprocessor or a CPU can do one thing. Only one thing. Anybody know what that one thing is? It can run a program. Period. Huh? It can do one thing. It runs programs. Who writes programs? People. People are the brains of the computer. They write the programs. Everything you see a computer do is being run by programs. This is a program called PowerPoint. Who wrote PowerPoint? People. So all the processor does is run programs. That's all it does. It goes. It's always in two phases. It's always in two phases. It's either fetch or execute. Fetch it. When it's in the fetch phase, it's pulling an instruction in, and when it switches to execute, what does it do? It does what the instruction told it to do. And you're in control of it. If you understand these things from the very time it's brought to life, it's under the control of the program. There's only one thing it knows, and that's to go to a certain place in the computer's memory looking for that first instruction. That's all it knows. And that's built into the CPU. And it better have an instruction there. If it don't have an instruction there, then that would be something happens to your autonomous nervous system. What is your autonomous nervous system? Yeah, it's what you're born with, right? You're born with your autonomous So, but we got once to get the programs into it, we got to have input ports. To get the programs out of it, well, that's not true. So usually what we do is we start off with this guy right here. What's it called? This is your autonomous nervous system. This is the programs you are born with. So every time you turn the processor on, where does it go looking for instructions? It goes right there. This is a read-only unit. I mean, that would be awful if these doctors could get in and change our autonomous nervous system. Well, this is your basic operating system. By the way, that's a term we'll use. An operating system is programs that make the computer operate. So this is an operating system I've got up here. This is Windows 7. It's an operating system. But this operating system is not in the computer's memory. It's out here on a hard drive somewhere. So when I turn this computer on, where's it born into? Right here. So there's ROM in this machine. It goes in there and hits this program right here, and then it starts coming to life. One of the things is that what some of the things we need to do. Well, we need to go in and check. Normally they run most computers now run a little, we call it POST, power on self test, just to see. So you'll see when we turn these PLCs on, the lights will flash, and what's it doing? It's just going out there running the basic power on self test. Initializes all the programmable devices in the chip, and then pretty soon it's going to tell it to go out and get its main operating system. Sometimes the main operating system is in the ROM. A lot of times it's not in the ROM. Like for this computer right here, the main operating system is not in the ROMs, it's on a disk drive. But what does the ROMs tell it to do? To go out there and load that operating system, right? Where does it put it at? Well, it puts it in this memory right here. This is called random access memory. Now, really, it's random access read-write memory, which means we can do what with this memory? We can put stuff in it, right? And we can do what? The processor can take things out. So a lot of your computers run like that. These guys, their operating system is in the ROM, which is nice because if I turn the power off, I could leave it off for a year, come back and turn it on, right? You understand? And it will go ahead and boot in its operating system. So we get the operating system certain different ways. This has nothing to do with mass storage devices. A lot of people get these mass storage devices confused. We got 6 terabytes worth of data on our file server over in the other building. Is that memory? No. So what you got to think about, and people get this confused all the time, is you got to understand it's like us using books. What do we use books for? To hold information until we get ready to use it. And then we read it, we load it into our RAM, right? You understand? We call it short-term memory. And then we process it, and normally when we're through with it, we just do what? Kick it out. And that's what RAM is. So computers use mass storage devices like USB thumb drives and hard drives and all this other kind of stuff, just like we use books. These are not memory. These are mass storage devices. We load information off of them into the memory of the computer, right? That makes sense? So, what does the ALU do? This is the guy right here. This is the arithmetic logic unit. And normally, most of your processors now, PLCs don't have that. PLCs don't do graphics. They don't do graphics. They don't need to do graphics. So that means most of your high-end processors, like your i7s and your i5s and your AMD processors, have a graphics ALU in there that handles nothing but what? Graphics instructions. Ours has an ALU. It probably only got one. PLCs are not very complicated computers. We do have, most of your computers now have multiple of these. We call them cores. I think mine's an AMD Amatron, and it's got 4 cores in it. So it's actually got 4 processors inside the same chip. Then we have what we call registers. Registers are just temporary storage locations we bring information into while it's being used by the ALU. So normally, if we add 2 numbers together, we would bring them into what? the registers would tell the process, the ALU to add them together, and then it usually stores it on register. And then if I want to put it in memory, I have to put an instruction that gets it out of the memory and puts it into the memory. Y'all follow me so far? Internal bus. Internal bus is just a bunch of conductors that everything connects to. So we share a lot of electrical conductors. Instruction decoder. This guy right here is taking our instructions that's coming in. By the way, what language does the processor understand? No, it don't understand assembly. It has no idea what assembly is. Binary. All this guy knows is ones and zeros. So all your we call this machine language. So microprocessors speak their machine language. That's what they do. Different processors have a different machine language. So it's just like you've got an Android phone. It has a different machine language than an iPhone, right? You understand that? So that's why I cannot download an Android application and try to put it in my iPhone, because the processor in my iPhone speaks a different language. It's a different microprocessor. Now, it might have the same instructions, but the codes might be different, right? Y'all understand that? So one of them to add might be 100100001, and the other one might be 0104. Understand what we're saying? So different processors speak different languages. So thank goodness we don't have to program in machine language. The first processor trainers that we got were machine language trainers. So we had to learn all these codes to do what? To tell it what we wanted to do. We call them outcomes. So this guy right here takes those binary instructions when the processor's in the fetch phase, and it says, okay, what are you telling me to do? Are you telling me to add? Are you telling me to do this? Are you telling me to do that? And then the processor will switch into what we call the execute phase, and what does it do? It does what the instruction was, or the code told it what to do. Cache memory. This was added. They came up in, we started off with two categories. The first memories they used was what they called static random access memory. Extremely high speed memory. But you might not understand this, but we have these devices called transistors. Everybody hold that. A static cell took about 5 transistors for every 1 and 0 I stored in the computer. So they said, well, let's see if we can come up with a better method. So they came out with a type of memory we call dynamic memory. Dynamic memory requires 1 transistor per storage cell. So it means if I've got a certain size of little old tiny die I'm trying to put this on, which one could I put more storage cells on? Well, static, 5 per cell, so I could put basically 5 times more memory bits inside a dynamic than I could a static. The problem with dynamic is that it's slow. It's a lot slower. And it's got another technique. It's got to be refreshed, and we'll talk about that later. So they had to come up with a method where going to this slow speed memory did not slow down the execution of programs. And the method they came up with was what we call a cache memory, which is, originally it was outside the processor. It was out on the buses. It was out on that processor. This became so popular that eventually they moved the cache memory inside the processor. So we have one that the cache is just holding stuff, right? Understand? So they have one that holds instructions and one that holds data. Now what they came up with, it was ingenious, is while the processor's working in here, then what the memory controller does is it goes ahead and prefetches instructions. So it might have 5, 6, 7, 10 that it can go out there and grab while the processor's working on the ALU. And then the next time it comes out, it don't have to go out to the memory. It can get it out of the water. The cache comes up here, hits the cache, runs out of cache, right? You understand? Has to slow down, come in here. Then what does the processor do? It goes out there and prefetches stuff, right? You understand? And crams them into these caches. So eventually, every program does what eventually? Anybody know? Yeah, every program I've ever seen loops. Even robots. We loop robot programs all the time. So what happens after one pass through the program, the whole dang program is now in the what? In the cache. Now the microprocessor screen. So while it's loading the cache, it's what? So the old days we used to do this. If you think about mailboxes out there, if you think about mailboxes, this is the way it used to work. And think about mailboxes as one address. The way it used to work is I would say, well, I need to go to address 0. I'd go out my house, I'd go out the mailbox, I'd get one letter out of there, I'd come back in my house. Now there's a 99% chance that I need the next consecutive address. Well, I'd come back in and they would say, well, Rich, you need to go to mailbox 1. And I would do what? I would go out and go to mailbox 1. I would get it and I'd come back to the house. And they'd say, well, Rich, you need to go out to mailbox 2. And this is the way it used to be until they came up with this feature. So now they say, well, Rich, you know that you need to go out to mailbox 1. Well, I'd go out to mailbox 1 and I'd get mailbox 0, 1, 2, 3, 4, and 5, and I'd bring them in. I would take 0 and give it to the AOU, and I'd put the other ones in the what? Cache. And then I hit the end of the cache, and then I'd say, well, I need to go out there again. And I'd go out there, instead of getting 1, I'd get what? Maybe 5. Bring them in, give him the 1, and put the other ones in the what? Cache. And then eventually what's going to happen? The program's going to do what? It's going to loop. So the only time you have hits, or if the program jumps, it has to reload. If it jumps into another sequence, you have to reload the cache. But once you're in a loop like that, these guys are screwed. And that's what has really allowed us to use very slow memory out here and then increase it. So now our microprocessors have, I think the i7 has 3 levels of cache. So cache 3 communicates with the bus. It loads cache 2. It loads cache 1. So there's probably a 90% chance that, and this guy's constantly prefetching. They have look ahead. These processors are very smart. They anticipate a jump instruction where we change the flow of the program, and they automatically start preloading the cache from where the processor is supposed to go.
Like my phone, like in your phone that has like cache and stuff. So it's kind of pointless for me to clear the data cache because it'll just reload everything.
Probably not. In your situation, it's a different type of cache. Cache is just where you can temporarily store data, and this is the same feature, but this is inside the processor. You would not have access to the processor cache. This is inside.
It's like on my phone, like clear up.
Yeah, you can. But that's just temporary storage. That's all it is. And that's the cache is the same thing. You cannot access the cache inside the processor. It's handled automatically. It's a good question. Any more? So instruction cache, temporary host prefetched instruction, temporary host prefetched data. I should have put prefetched. So this is actually the die. The die is what they actually use to make the processor. This is an i7 processor. It has 758 million, approximately 758 million transistors. This is our cache down here. I think this is level 3 cache. This is a quad core processor. So each one of these are cores. What's a core? Used to, what they realize is there's certain sections of a program, a big long program, that can run by itself. It don't have to be part of another program. Over time, this is what we call a thread. So they came up and they said, and what they originally did is we put multiple microprocessors inside our computer. So our first big server we have over there, if you looked at it, it had 2 microprocessor slots in there. So we put 2 microprocessors in that thing. And if you had an application, which most of them are now, they're called multi-threaded applications. What happens is that the memory controller inside the computer would assign each thread to a different CPU. So you could, on this guy, you could have up to 4 threads in the same application running at the same time, which is different than multitasking. Anybody ever heard of the term multitasking? Well, multitasking is when we run multiple programs, but we share time between the programs. So that's even true now. So you get 5 or 6 programs up on your computer at the same time. What happens to all of them? Slow down. Multi-threads only deals with an application. If the application is written correctly, then when this thing loads in, what can happen is the memory controller inside the CPU can assign each thread to a different core or different processor. Well, that's what they finally said. We said, why split these processors up on the motherboard? Why don't we just go ahead and put, since we can put all these transistors in there, why don't we just put multiple processors inside the same unit? And we call these cores. So the i7 is a 4-core processor. Now, if you run a program that is not multi-threaded, it's going to be assigned to 1 core. This only comes in if you run into multi-threaded applications or multi-threaded operating system. Everybody understand that? If you get a multi-threaded operating system or a multi-threaded application, these guys will scream. Which means you can run spell check. You can go ahead and run spell check and load it in, right? You understand? And then you can have a Word document up there. Spell check is all the way over. Used to, when we first got word processors, we would have to write the program and then we would have to tell it to check the spelling. But if it's a different thread, then it can be assigned its own what? On processor. And what happens now? I mean, you're up here typing something on your cell phone and it'll come up here and show you it's what? It's spelt wrong, or it can come up and give you, I hate that autocorrect. Anybody that takes Nancy classes, she's got a real good story about it. So here's the block diagram of an i7 processor. So it's got how many cores? Each one of them's got their own L2 cache. Each one's got their own L3 cache. They share one of them. I can't remember. And then it's got these things we call buses. Now, does PLCs run multi-core processors? Probably not. Because the programs that they run does not have to be the same applications you would run on a computer. Now, what kind of applications do we run on a computer? Some pretty hefty things, right? Especially gaming. Gaming is really, you play games on your computer. Now, what we do, and I've reworded this a little bit out of the book, so what we do is we split what we have. Coming out of the microprocessor, we have 3 buses. We have what we call an address bus. And what's the address bus used for? It's just like when I want to send you something, I'm not talking to your address. I use that address to do what? Select you, right? Everybody okay? Then we have the bus called the data. Now, the more conductors we have assigned to the address bus, the more things the microprocessor can select. That makes sense? Then we have what we call the data bus. What does the data bus do? This is where the data is actually transferred between the device selected by the address bus. Everybody okay? So first of all, everything in the computer is assigned an address. And it's a binary address. And this is built into the computer when whoever engineers the computer. They decide where everything's at. They can't decide where the ROM's at because the processor goes to a certain address every time you start it up. So every computer has an address it goes to. If you're an engineer, you have to make sure you have ROM at that address. Then after that, you're usually in control of that. Usually your ROM is up in your high addresses, and then down below in the address and range, that's where your RAM would be. Then we have a bus that the book don't even talk about, but it's very, very important. It's called the control bus. The control bus controls the flow of information between the selected device, and the what was selected by the address bus. So the number of conductors we have assigned to the control bus would determine how much control we have over that flow. That makes sense. So This is basically a makeup of a microcomputer. This is drawn as a bus. I'm going to show you the next diagram here in a second. So we have the microprocessor, we have the memory. The memory is divided into two categories. It has raw and RAM. Then we have input ports and we have output. Things that are connected to, in computers, the things that we connect to these ports, we call peripherals. In PLCs, they call them field devices. Now, why they do that, I don't know. So that's one terminology that's different between computers and PLCs. So peripheral means on the peripheral of, right? You understand? Anything that communicates with the computer through a port is a peripheral. For PLCs, we call them one, field device. So if I hook up a switch, that's a field device now, right? That makes sense? This is a light. This is a wire. This is a field device. Now this is out of my book. So this is a pretty good example. So we got the microprocessor. These are the conductors that represent the address bus. I've only got 3 address bus. That means I can select 8 different things. Now the way the address bus works, it works using binary. And let's talk a little bit about that. Anybody know about binary? Tell me. Somebody said, Binary is binary is a number system, which means number system means we can count with it and we can do math with it, right? And what we do is we use, and this is going to be in the next chapter, by the way, or the next lecture. The next lecture we're going to talk about is called numbering systems. And the primary number system that a processor uses, and also the PLC uses, is binary. Now, it's not going to make, we're not going to use that a lot in this class, but if you take the advanced PLC class where we start having to do logic and stuff like that, then the binary number system really makes sense. Here, this is a computer. One thing that a computer can do is it can translate that. It loves translation. And translation means I can do it one way, and then it can be translated into binary, right? I understand that. So we're not going to communicate with our computer this semester. With binary, we're going to communicate basically English. Okay, we go? Okay. Just to get a little clearer. Well, when the binary number system, by the way, anybody know what we call the digits in a binary number system? We call them a bit. They're called bits. And in binary, a bit can only have 2 states. It can either be a 0 or a period. That's all it can be. That's what binary means. Binary means bi means 2, right? So in the binary number system, our digits can only have 2 combinations. That's either a 0 or 1. Everybody okay? Now, when you learn how to count, how did y'all learn how to count? Well, let's say I wrote down 1,968. How did you learn that? What do we call this guy right here? This digit right here. We call it units, right? We call this what? Tens. We call this hundreds. We call it thousands. Now, the true way it works, any base, the way it works is this digit holds a weight of the base, and we call it the base because it's an exponent. So an exponent, the number you raise to a power is called the base, right? You understand? It would be the base raised to some power. That digit right there is always to the 0 power. Any number raised to the 0 power is, don't y'all say 0? 1. Any number raised to the 0 power is 1. This would be 10 to the first. This would be 10 to the second. This would be 10 to the first. Next one would be what? 10 to the fourth, 10 to the fifth, 10 to the sixth. Now, if I raise 10 to the 0, it's going to be 1. 10 to the first is going to be 10. 10 squared is going to be 100. And this would be 1,000. And that's the way you learned it, right? But you need to learn this because now you can do any base. Okay? So to find out the weight that this number had in the number, I would take this and multiply it by either 10 to the third or I can multiply it by 1,000. So it holds a weight of 1,000. This holds a weight of 9 times 100. What's 9 times 100? 900. This holds a weight of 6 times 10, which would be 60, and this would be 8 times 1, which is 8. Y'all got the bases of any base. Binary is a base 2. This would be a weight of 2 to the 0. This would be a weight of 2 to the 1, 2 squared, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, 2 to the 9th. Everybody okay? Okay. So let's write down a binary number, see if we can figure out what the weight is, or the value. So let's do 0, 1, 0, 1, 1, 0, 1, 0. Is this a big number or a small one? Looks like a big number, but remember, they only have 2 combinations. This would be 2 to the 0. What's 2 to the 0? What's 2 to the 1st? What's 2 squared? 4. Now what we're doing is we're writing down, we're going to take this to decimal. So this does not hold a weight of 4. It holds a weight of 2 squared. But what we're going to do is we're going to take this number to decimal. So what I'm doing is I'm writing down the decimal equivalent of the powers of 2. Now we're off and running. So what would all you have to do is just double every time. What's 2 times 8? 4? 8. This would be what? 16, 32, 64. Now I'm only interested in the bits that have 1s on them. Because if we're going to do the same thing. I'm going to take this and multiply it times that. Right? You understand? So I'd say this would be times that. Well, what's 0 times any number? So it has no weight in the number. So all I'm going to do is write down the decimal weights of the numbers that's got 1s in the bits. So I write down 64. I'd write down 16, I'd write down 8, and I'd write down 2, and I'd add those together. And that'd give me the decimal weight of that number. What would that be? My 8 don't look too good. About 80? Huh? This is only a 7. What's this do? We got 9. So that would have a weight of 9. And that's decimal, right? Y'all see that? So what we would do right here is the only combinations I could put out my address bus. I could put out 0. I could put out 1. I could put out 2. I could put out 3. I could put out 4. I could put out 5. I could put out 6. And I can put out 7. Oops, that's not a 7, Rich. Duh. Everybody okay? Yes? No? So how many addresses could we legally put out? 1, 2, 3, 4, 5, 6, 7, 8. Well, what you can tell, what we could have done, and what you can do to tell the number of combinations, you can just raise 10 to the number of digits, and that tells you the number of combinations. So it means in this one, this is a very small address bus. I've got 3 lines that handle my address, which means I could only have 8 mailboxes out there. So count my mailboxes out there. I got what? 0 through 7, right? Now my data bus, this is representing my data bus over here, and I've got an 8-bit data bus. So currently microprocessors, I think the i7 has like a 35-bit address bus. So 35 bits means that processor can put out, let me find my calculator. I think i7, they don't like to give out very much information about their processors. So let me go up here and go to scientific. I'm going to do 2. Where's my, oh yeah, no, where's my raised to the power? Oh, right here, 2 raised to the 35th. So this is how many addresses that the i7 can put out. Which would be around So the size of the address, the number of lines you have on the address bus determines how many addresses the processor can put out. I've only got 3 because this is just an example. Now, what we have down here is I've got mailboxes, and that's all we're trying to do. Very, very simple. Is I put out the address up there. That's address 4. That's a 4. You know see it? Right? Can you see it very top? Right. That's a 4. This goes down here, and every one of the mailboxes see that address. Every one of them see. But what we have out here in memory, we have these circuits that we call address decoder circuits, and that's all they do is they're sitting there looking at the address book. And when the combination comes out, then they enable that device. So notice which mailbox door is open. 4. This makes sense. Now, what can we do with a mailbox? Well, I can either put information into it or I can take information out. So we got to tell our memory or our I/O device or our input or output device, what do I want it to do? So what bus does that? The control bus. So up there it says, I'm writing. So it tells this guy right here to take whatever information on the data bus. So the processor will get information. Now, every one of these devices are connected to the data bus, but only one of them's got its what? Its door open, right? Does this make sense? So it would take that information and store it inside it. And then it's through. Put another address on the address bus, this door opens, this thing closes, and another one opens. So this would be an example of what we call a write cycle. A read cycle is exactly the same thing. Except here the control bus says, now here we're writing the address 6. So mailbox address 6, 110, open. But then we got to tell the mailbox what we're going to do, and then the control bus tells us that. So the more conductors we have that's defined to the control bus, the more control we have over our communication. The more lines we have on our address bus, the more things we can do what? Select. The more lines we have on our data bus, the more we can communicate at any one time. Current processors run 64-bit data buses. And that's why we call them, y'all heard the term, it's a 64-bit processor. That's what it means. It runs a 64-bit data bus. Originally we came out, the first processor came out, I forgot what it was, a 4004 put out by Intel. I can't remember the size of the address bus, but I know the data bus was 4 bits. And then they came out with the 8008, which was an 8-bit data bus. And we dealt with 8-bit processors for a long time. And then we jumped up to 16. So when they say a 16-bit or 64-bit, they're not talking about the size of the address bus. They're talking about the size of the data bus. So a 16-bit processor means it's got a what? It's got 16 wires that belongs to the what? The data bus. 64-bit processor's got 64 bits. And a used address bus. So you ought to see some of the electrical connections on some of this processor. I don't know what's in this one I brought in here. We'll pop it off and look at the processor. It's an older motherboard. So we have 2 types of microprocessor. We have CISC and we have RISC. Anybody heard that? Anybody know what those are? What does the book say?
Apple use RISC.
Huh?
Apple use RISC.
Well, Apple uses different processors. All depends on what they do. Originally, we had individual instructions that did everything. We had to have so if I wanted to perform a very complex task, it might take 15 or 20 instructions to cause that. These are what we call CISC processors. This is what we first did. These are complex instruction set computers or computers. Then as the processors evolved and the internal works of the processor became more complex and the AOEs became more complex, all of a sudden we could do more complex tasks with single instructions. What do you think the RISC stands for? It's a reduced instruction set computer. Most of our processors now are RISC processors. And it used to be when I first got involved with microprocessors, which was the first one I got involved with was an 8-bit processor put out by Motorola called the 6800. We went up to the 6808. It was an 8-bit processor. And how much math could it do? It could add and subtract. That's all it could do. So how did we make it divide? I had to write a program that made it divide. The first thing we did was repetitive subtraction. We start subtracting the divisor from the, what do they call it, the dividend, until we generated a bar. And then we'd keep up with the number of times we went through that loop. Subtraction, we had to do division. We did multiple subtractions. Then we learned how to do shifting. It was pretty neat. But it took multiple instructions to multiply. It took multiple instructions to add. It took multiple instructions to do square roots. So we could do it, but we had to do it with a lot of instructions, right? You understand? The program to do multiplication, especially if it was a catch-all multiplication, you wanted to do big math. These guys were very, very complex just to get the dang thing to add. Now these were CISC processors. Well, eventually what did they do? Well, they added multiply instructions to the instruction set, but the processor had to become more complex to do the multiplication. So now instead of me putting 50 instructions to tell it to multiply, I could do it with what? 1. Instead of doing 50 instructions to tell it to divide, I could do it with what? With 1. So this is when we started moving into RISC. Everybody okay? I lost anybody. So this is in the book. They don't tell you what CISC stands for. They don't tell you what RISC stands for. So what does CISC stand for? Complex Instruction Set Computer. And RISC stands for what? Reduced Instruction Set. And it's just putting more complicated circuitry inside the ALU that allows it to handle these instructions. Okay, guys, y'all take a 10-minute break. Big old binary number. And I'm trying to tell you this number. I'm trying to get to, let me go. Okay, here we go. So I'm talking about a 64, the data bus, there would be 64 of these things. I'm not going to go that far. Now, how many of y'all could write that down? You could, for about, what do we have? We can't. I'm laughing because I had one of my students said he had a photographic memory. He came up and said, Mr. Ryman, you told us that that we need to study these questions on these tests, and these were the questions that would be on the final. He says, I have a photographic memory, and he says, these questions wasn't on the test. And I went and showed him his previous tests. I said, here's this one, and this one. I can't remember his name, but I said, I guess you must have forgot to load your film that day. Don't need to laugh at me, I'm the instructor. So if I was to come up here and take this, and I'm going to split it up into groups of 4s. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And I'll present there's a 0 there. And I wrote this down 5A, C, A, 5E. How many could write that down correctly? Just about all of you, right? And what I just did is I went from binary over to a number system called hexadecimal. And I did it on the fly. I didn't even think about it. And but it gives me the ability to transfer to you very large binary numbers using fewer digits. And you could give me a hex number and I could give you the binary equivalent. So your computer displays a lot of information in hexadecimal. And your PLC likes to do that too. And it displays extremely large numbers that it don't want to put out there that long, that it needs to do it in fewer digits. And it'll use a base called hexadecimal. Wasn't that cool? Didn't he pull out a calculator? Didn't do anything. So you can go between hexadecimal and binary just by learning patterns. And that's what I did. I know patterns. How many patterns did you have to learn when you were in elementary school? Y'all know what multiplication is. What's multiplication? It's repetitive addition. So I could say 5 times 5. I could add 5 to itself 5 times. But what did we do to keep from doing that? We learned multiplication tables. So instead of me writing 5 times 5, which is what multiplication is, we learned that 5 times 5 is what? 25. How far did you have to go with your multiplication tables? 12 times 12. And for going from hexadecimal to binary, you got to learn 16 patterns. 16 binary patterns. That's all you got to know. 16. And one of them, 0. So this 4-bit pattern equals 0 in decimal. So that's one. So basically you got to learn 15 patterns. 4-bit patterns. And you can go between hexadecimal and binary just like that. Or you can use a calculator and let it do something that you should do. So a lot of the information that our computer displays to us, it's going to display in hexadecimal. So everything in this computer is assigned an address. And you've got access to it, guys. I can come over here and I can go to Program Files. And it's a little harder to find in Windows 10. I'm going to go to Accessories. And then I'm going to go to System Tools. And then I'm going to go to System Information. And this tells me every address within this computer. So I'm going to come over here to Hardware Resources. And I'm going to go to Memory. This is the memory addresses that's assigned inside this computer. So this is everything in the computer. This is the actual binary address, but it's not going to give it to me in binary. It's giving me to me in hexadecimal. But if I needed to know the binary addresses, I could rip that sucker off in a heartbeat. Right? So your computer is binary, but computers process information. This is nothing but a bunch of dots. And all it's doing is it takes a binary number and it figures out what dots to turn it on. It can display anything. One of the big things a computer can do is process information. It can make one thing mean another, right? You understand? So sure, it can take a big long binary number and display a 1111 and says, okay, a 111 means this pattern. It throws that pattern of dots up there and displays it out. So here, this is all the addresses for all the memory inside this computer. Big old addresses. Each one of these are 4 bits. So just think about that. Here's the input-output addresses on this thing. And what base are they using? They're using hexadecimal. So I could find the system clock. I could find all this. Here's the graphics. Here's the actual graphics controller inside this computer. That's the address right there. But now I don't know that. I like to let my computer take care of a lot of this stuff. Every address in the computer is a binary address. So are we going to use binary addresses when we select that output port right there? No, we're going to use what we call a logical address, where I say input 0, and then it says, okay, input 0 is at 00110000, right? You understand? It translates that for us. So when you deal with high-level languages, it allows you to use English, but it's got to be translated, because the only language the processor understands is what? Zeros and ones. But we can very easily translate it. You know, the Bible was originally written in what? How many times has the Bible been translated? A lot, right? It's probably the most translated book that's ever been out there. So RAM and ROM, we're okay with that. So what's RAM? Random access, and I like to add read-write memory. So this is the memory inside the computer that we can use. This is like what we call our temporary memory. Temporary memory is where you bring stuff in, you use it, and then you do what? Then you kick it out. You're through with it. And we do a lot of that. We use that temporary memory. It's hard to get stuff into our long-term memory, which would be kind of like ROM. It's pretty neat. We can actually redo our ROM. We can add to it as we go along. But you are born with your autonomous nervous system. Read-only memory, which is kind of, we'll talk a little bit about what's going on here now. Used to read-only memory. You bought these. The actual machine language programs was built into the chip when it was made by the manufacturer. So let's go on. We'll talk about it. So we got two types of RAM. We have what we call static RAM. It's extremely fast. It uses bipolar junction transistors, which are extremely fast, but it takes about 4 transistors for every bit. I'm 4, 5. I just did that to see if you was paying attention. About 5 transistors per bit. Dynamic takes 1 transistor per bit, but it's real slow. So the mass memory, the mass RAM inside your machine is usually dynamic memory. The caches are static memory. And that's what's got us, that's what allows us to do that, is those dang caches, because the processor, the memory control unit inside the processor is constantly doing what? Loading those caches. 3 levels. So level 3 feeds level 2, level 2 feeds level 1, and there's probably a 99.9% chance that what the processor needs is in the cache. So the processor, these processors now, as smart as those memory controllers are, they can prefetch. They have what they call branch prediction. They branch when they calculate. They see a program change instruction come into the processor, and they automatically start loading the cache with where the processor is going to. This is why we got these extremely high-speed processors, because of those caches. It took them a little while, and they're so prevalent in today's processors. Some of y'all might have already heard this. So DRAM, we have is evolved into something called double data rate, DDR. Y'all heard that? If you ever had to upgrade the memory? DDR, we're up to DDR. Started off with DDR. Some people call it DDR1. We're up to DDR4 right now. So that's the fourth generation of it. And it's synchronous. Synchronous means, originally when the DRAM first came out, it was asynchronous. So it was not synchronized with the clock. Now it's synchronized with the clock. What they did with DDR, it's called double data rate. It can transfer information on what we call the rising edge and the falling edge. So basically you get twice the throughput of the clock at this time. So it's called double data rate synchronous SDRAM. I think we're up to DDR4, which can do about 33.37 megabits per second or something like that. And that's dynamic RAM.
I think they have DDR5.
Really? That's something I they might. If it is, I hadn't read up on it. So. And then, of course, static RAM, this is your cache. The problem with DRAM, these act like little batteries, little tiny batteries. And what happens to batteries if you don't use them? They die. So these guys constantly discharge. We charge them, we discharge them, we charge them, we discharge them. So what we have to do all the time with the DRAM, but as long as you go out there and charge your battery, right, you understand, so these are rechargeable batteries, then they'll never go down. So we call that, in DRAM, we call that refresh. Originally it was done by programs, but now DRAM has been around so long it's done by the hardware inside the machine. The machine automatically has the circuits that refresh the DRAM for you. But while it's being refreshed, you can't use it, right? You understand? So that's one of the reasons DRAM is a lot slower, but it's so much cheaper per sale. We okay? Mask ROM, this is what I was talking about. These mask ROM, this is programmed by the manufacturer. If they want to upgrade your ROMs, what did you have to do? You had to buy them. Yeah, they'd have to send you another version. Now, what they came out with after that, and we got one around here, I need to go down and get it. We came out with a special ROM called PROMS. What does PROMS stand for? Program Real Unit. Now, everybody knows what a fuse does. What does a fuse do? It blows. So that's basically what PROMS were. It just had millions of little fuses in there that you started out with all zeros stored in there, and then if you blew the fuse for a bit, it would turn it into a what? 1. But what happens when you blow a fuse? Yeah, so if you made a mistake or you needed to change it out, you'd have to get a new PROM. And by the way, this became known as burning. So we burn a new chip. We need to burn a ROM. And after that, most people use this for all these programmable things. So PROMs. So these ran around for a long time. But these were still one-shot devices. Then they came out with a type of memory called eraser. Anybody know what? Yeah, these guys are, most of the chips on this guy are sensitive to static electricity. So if you ever handle one of these things, you either use a wristband, an anti-static wristband, I'll show you that, or you handle it by the edges. This motherboard is not really good anymore. You're not going to put it in anything. Of course, it might work. We had a girl that came to school here, and her house caught on fire, and it burned her house up. And she brought her computer in here, and it got so hot that it melted the integrated circuits off the disk drive, and the motherboard was just as black as it could be. I took the mother home and put it in my dishwasher, washed it off real good, dried it out real good, fired that sucker up, and guess what? It worked. It was amazing. Janice Phillips was with me. I felt sorry about losing her house, but I was amazed at the motherboard. So this is our processor right here. It's usually and even on your laptops. And this is why tablets, little tablets, can never have the speed that these guys can have. Because the more speed you have, the hotter these things get. These processors can put out anywhere from 75 and 100 watts worth of power, heat. That's hot. So we need to get that heat away from semiconductors. Semiconductors don't like heat. So normally what we do is we mount these big old things on top of them called heat sinks. And they got a bunch of blades on it to increase the surface area. And then also to increase the efficiency. What do we put on it? We put a fan. So the processor's under here. I don't think I got a screwdriver. And these processors are designed to go into a certain socket. So here's the processor right here. I'm not going to let you handle this. So this is the microprocessor right here. Now what are these pins? We call these pins even though they're technically not. Address bus, data bus, control bus, and power. We forgot about the power bus. So actually there's 4 buses on the computer. It's a power bus. So a lot of these pins are power, right? So that's the processor right there. Now these guys fit into a certain socket, and so they'll come out with several variations. So they got several variations of the i7 processor. If you got these motherboards like this and they can support the speed, then you can upgrade the processor. It's got the same socket, right? You understand? You can upgrade the processor without upgrading the motherboard, which has become a very popular. So this is the actual processor. You ever saw a microprocessor before? Good. Then what we have is we have the control logic. We call these bridges. So this bridge is between the speed of the processor and the speed of the RAM, and then all your I/O. Your I/Os run real slow. They still run around 66 megahertz because I/O is not fast because they're out there with me and I'm not fast, right? You understand that? So the I/O bus on these processors usually run around 66 megahertz. And to go from gigahertz to megahertz, you go through a chipset. So this is the actual chipset right here. This is motherboard put out by Gigabyte. Then we start getting into, this is the socket for the RAM. This is DD RAM. This looks like it's a DDR2. And they're not compatible with each other. What they do, y'all can see this little hump right there, we call it a key. Even though they might have the same pins, what they do on different DDR means they move the key. So that means you can't put a DDR3 into a motherboard that's designed around a DDR2 or vice versa, because they change the technology, right? You understand? Then we get into, this is where the power supply hooks up. So we have a power supply in a desktop, and it's a big unit. So most of them around 400, 500 watts of power. So these guys are full blown, devices. I can't run, 2 terabyte drives off of a laptop, but I could off of these power supplies that we have in these machines. This is where we hook up the power supply. And then we start, this is an older port. This is the what we call a parallel ATA, which is, I don't know if y'all remember, but used to, if you ever looked inside the computer, your disk drives had big old fat cables on them. They have 40 pin cables. Those are what we call IDE cables. They were parallel. It was a parallel interface, and this was IDE. We could hook up two drives to this, but we had to do what we call a daisy chain. So we had a jump between the two. What they did, this used a technique we call single-ended, which we're not going to get into. They came out with a new interface they called differential. And what it did is it gave them the ability to triple or quadruple the speed of serial communication. Now, parallel means would be like the interstates going up to Birmingham. And parallel would be we've got multiple lanes that they keep wanting to do what? Add more to. I think they're doing that down to Alabaster now. They're going to 8 lanes. So the more lanes you put, the faster you can send the information, right? You understand. But the more expensive the interstate comes. I could drop down to a single lane, right? Put them this way and that way. I could still get 1 million cars to Birmingham, right? You understand? But it would take what? But the 1 lane road would be so much cheaper than the what? Than the 8 lane road. So the advantage of serial over parallel is that it's so much what? Cheaper. And as long as I'm dealing with peripherals that don't, like keyboards, why would I need parallel information to a keyboard when I'm the one that's out here typing on it? So I got my Pico processor running over here at 2.6 gigahertz, and here I'm typing like this, right? You understand? Even on your cell phone, you're doing your finger like that. That amazes me. You ever see Rich text? It's like, and I can type. I can fly on these things. But you get these people doing that with their fingers, it amazes me. I don't know how they do it. My fingers are too big. I usually hit 4 letters anyway. So keyboards are serial. Display is sort of serial. But what they did when they came out with differential, they quadrupled the speed. So this is what we call serial ATA right here. And all you do on these is you put 1 drive per connector. Just 1 drive or 1 device. It could either be these are internal, which means these can't leave the computer. These are designed to be external, so we can hook up serial ATA outside of the computer. These guys are amazing. And now they still are fast enough to handle the fastest hard drives that we have there. You can only spin the disk so fast. The fastest that we can spin those disks in there is like 7,200 RPM right now. And that gives us a transfer rate. And they put cache memory on there just to try to keep up with the processor. Even serial ATA is idling at the speeds that the disk drives can go. So this is going down. This is where these are called expansion slots, which mean we can add additional ports to the machine. You don't get that on laptops. You get that on desktops. You can upgrade. This is the video interface card right here. This is a PCI Express, which is the last technique they came up with as far as internal video goes. And everybody knows what these ports are. What are these? USB. This is Ethernet, right? This is sound. This guy handled 3 sounds. You had mid-range, you had front, back. This is the old video interface called VGA, which is still popular on projectors. Most of our video is gone either HDMI right now, or it's gone to what they call DVI, digital video interface. This is the old COM port, which has disappeared. USB is taking the place of these. But this is still popular with Allen Bradley. Sure is. So what we have to do on Allen Bradley is we have to do what we call a dongle, which is a go-between. And we plug it in here. And what it does, it converts USB over to the old RS-232 interface. So Allen Bradley still likes the old thing. They call it the data highway, by the way. And these are the old mice and keyboard ports. These are these are not the ports. These are the connection to the ports. The actual ports are inside the chipset. So these are connectors. People call it ports, but this is not the port. This is the what? This is the connection to the port. One of them was mouse, one of them was keyboard, but you look at them, they're exactly the same. Yeah, these are PS2. Yeah, this came out with a PS2. This size keyboard. And the big problem we had all the time was people would confuse the mouse port and the keyboard port. It didn't hurt anything, it just nothing didn't work. So eventually they started color coding. So if you bought an old keyboard for this, it would be colored, it's colored purple, right? I don't know. One of them's colored purple, one of them's colored green, just so you plug them into the right port. So this is a standard. We call this a motherboard because it's the mother of all boards, right? And this is what you still get on desktops. Now the advantage of desktops, guys, when I go home, I put my tablet up, I put this laptop up, and I go into my nice desktop computer. It's got like a 24-inch display on it, right? You understand? Or more. It's got a quad core AMD processor. It's got 8 gigabytes of RAM, and it screams because it's got the processing power. So you still can't beat a desktop as far as speed. You don't say something. So and when I go over to my office, I use my desktop over there. So these guys here are great. They're really convenient. Tablets are awful. I hate soft keyboards. I hate them with a passion. So, but anyway. So this is and now we got to take all this. If we start reducing it down, then what do we sacrifice? Speed. Yeah. Sacrifice speed. Now, what they did, and it's still very, very popular, a PLC is pretty expensive. So we have another for applications that I need to control, that I'm not going to change the program very often. We use what we call a microcomputer. And then we combine it and we end up with a microcomputer. So one of the most popular is one we call the Arduino. Have y'all heard of that guy? I'll show y'all one. And let me show you the price of these things. We use a company called Jamico to buy a bunch of our electronic stuff from. And this is a microcontroller. How much you think it costs? Or microcomputer, I'm saying. Microcontroller, huh? Pretty close. You've dealt with them before. I think www.jamico. So if you're into electronics, this is a good place to go. Get that in the key. And then we'll search for the Arduino. No, I don't want that. Thank you. Where'd it go? So here's a little microcontroller called the Arduino. $23, 23 bucks. So what it uses a microcontroller chip. I mean, this guy's only this big. This is pretty close. So here's the actual microcomputer right here. So everything's in there. It has the CPU in there. It's got a RAM and ROM, and the pins are act like ports. So the ROMs and everything's inside. Here's our, it's got this many analog ports. This is where I hit power, reset. These guys right here are programmable. You can program them with digital input, or you can program them with output, or you can program them with out. This guy right here, $22. Or $23. If you buy one, you know, the more you buy, the cheaper it is. But these guys program in a language that's pretty close to Pascal. It's a text-based language, very complicated. So this is not what we want, right? Not unless you got this guy right here, $23. Got how many output? 0, 1, 2, 3, 4, 5, 6, 7. We lose these transfers. So basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That you can program them to the input, you can program them to the output, or you can program them to be bidirectional. But it's very complicated to program. This is a program that I wrote to, but you're going to run it. So if I've got a small application, I don't want to go out and buy a $500 PLC to do something that's going to do the same thing all the time. I never want to change the program, right? You understand that? So this is where we might bring in a microcontroller and get somebody that knows how to program. So this is a program that pros. The application, by the way, to write the program is free. So I've got a 100-step stepping motor. So this is what you have to learn. They ask for donations. Takes a little while to do. So I'll write a program in English. And this is pretty close to Pascal, by the way. So this is kind of a hybrid Pascal language. It's not easy to learn, but it's still a lot better than trying to learn binary, right? You know what I'm saying? We've got 3 of these. So I've got one that I'll show y'all where we actually control what we call a stepper motor. Stepper motor is a motor that moves in steps. It's really, really neat. You can control it. So this is, they call them sketches. And here's the program. But if I was a computer programmer, this guy, just learning this language would be a snap. If you were an electrician, you'd probably cry a lot. So you'd have to have somebody to do this program for you. This is really, really close to Pascal, guys. So this is a programming language that I think did they teach Pascal here? Anybody know about Seattle? I know they teach Java, which is for programming what they call ActiveX control. They used to teach Visual Basic, which I was really good at. I was pretty good. I don't know if they did Pascal. By the way, all this is comments, so Rich can remember what his comments are. So we have to set up the port, we have to program the port, we have to say, I'm using this pin that's called frequency, I'm using it for what? Output, set up the speed of communication, 9600 bits per second. Set frequency equal to what? 13. So down here it uses 13 instead of frequency. So I'm setting up pin 13 to be a what? An output. Then I come up here and do a little math. Bring information in. This right here brings information in from my keyboard. Converts it over to a digital number. And then I generate a pulse. write to this port, and I'm going to make it go what? High. Then I turn around and give it a 10 millisecond delay. And I write to it and make it go slow. So this guy's going to generate a clock. Now this is what would be required to program a microcontroller. You have to learn a language like this. Now what we're going to do is we're going to use a language called ladder language, which is a graphical language. That's what we'll start in later on. So graphical language, a ladder diagram is that we start off with two rails. Oops, let me get back to my PowerPoint. And we looked a little bit at a ladder. I would start off with this. That's on there automatically as soon as we create a program. And then I would come over here and I would start putting in symbols. What's that a symbol for? Anybody know? Normally open contact, right? And then I might come over and do this. And then I would come over here and maybe do this. And then I would assign logical addresses. Makes sense? So I would come up here and I would say like N. So what type of port would that be? An input port, right? And then I come up and put something on. Allen Bradley would put something like this. Oh, I'm sorry, messed up. Now this is not the binary address for the computer. This is the logical address. It allows me to use a logical address. In fact, the actual logical address would be input, then I'd put a colon, and then I'd put 0/0. Now what that would do, it would tell my PLC to come up here and use I left my camera. It would tell us to read this in whatever's on this port right there. It's a digital port, so it's only to give me back a what? A 1 or a 0. But I'm doing it using symbols that I learned in motor controls or in this class. And I'm doing it in what we call a high-level language. Everybody okay? This makes sense? Now this computer right here has no idea what that symbol is. So what do we have to do? We have to put or translate. It has to be translated. So what happens, and we're going to program this with an application. The application, we're using the MicroLogix. Allen Bradley's got a new version of their programming application out. It's called RSLogix 5000. We're not teaching that. That's not the newest one. We're using a programming language called RSLogix 5000. And it's an application. I load it up on my computer. And what it does, it allows me to create programs using these symbols. And then I have to download it into the PLC. Well, what it does is automatically when I download it, it translates it from what? From this language over to the binary language that the processor understands. So this guy right here, all it does is binary. That's it. And then if I upload one, I can take a program in here and I can upload it into the application and then it'll translate it from what? From binary over to the graphical language. And that's the language we're going to use. So we learn programming language. This language that we're going to teach this semester is the most popular language used in PLC. There's actually 4. The most popular language used in PLCs is what's called ladder language, ladder diagrams. And you can see why it's got that name, because I create my circuits between something that looks like what? Looks like a ladder. What do you think we call these things? Call them rungs. We call rungs. Now, if I wanted to go to an output port, I would come over and start with O, which says what? Output. Then I'd put a colon. Then I would go on this one. All you got is 0. 0. So this first number defines the slot number. This would be slot 1, this would be slot 2, this would be slot 3. So if I wanted to add this an input port on this guy, I would say N1/0, and that would give me bit 0 on this guy. If I wanted to address an input port on here, I'd say input 2, right? Input colon 2/0. So the first number tells us the the slot. The second number tells us the bit within that slot. That makes sense? Very good. If it was an output port, so this guy right here, the output port is in slot 2. The CPU operates slot 1. So this would be slot 2. And I say I wanted to address bit 4. Then I would say out colon 2/4. Now this is a logical address. The actual address is a binary address, right? You understand that. But they understand that I don't understand binary. So they allow us to use logical addresses. That's fixed into the configure. But I could have used any one of those addresses, so I can change these logical addresses, right? Understand? So that's the language that we're going to learn. It's called ladder language. We'll let y'all look at some, we have what we call structured text language, which is basically what the Arduino uses. This would be a language that somebody that's used to writing computer programs, they would fall into this, structured text language, that fall into that just like you. It would be hard for them to learn ladder logic, but it would be easy for them to go into structured text programming, right? You understand that? Then we have people that comes up through electronics. They understand digital symbols. So we have a programming language called function block language. And so those guys can write programs using nothing but symbols for logic and ands and that kind of stuff. So it's evolved to support. Originally, the languages were set up to support people who came up through the electrical trade. And that's where ladder language came in. So that diagram we looked at last class, that was an electrical thing. But I could take that in a heartbeat now and do what? Program into a PLC. We'll try to do both of them. We'll try to do it in a PLC, and then we'll hardwire it for you, and I'll let you see. We're not going to save anything with the PLC because we'll still have to have the same number of push buttons, but you can see how we can program it into a computer. Any questions? So this is basically what they say. This is what the book is. This still in the book, by the way? Discovery. This is not quite right. This is actually what we call an AC input port. So these guys, so they're putting 120 volts AC. And then we come over here. This is called a rectifier. What do you think a rectifier does? First what? AC. And then it comes over here. This is called a Zener diode. And Zener diode basically sets the voltage to a precise voltage. If you put that sucker like that, it would blow up that Zener off. So we got to protect that. And this would make the input resistance of the actual input port be equal to nothing. We want this input port to have resistance, right? You understand that? Right now, there's almost no resistance. So an actual true AC input port for a PLC actually looks like this. So what did we add to the middle? We added these things. Anybody know what these are? So now we've protected everything inside there. So this is the true, this is an AC input port. So the only thing your computer understands is DC. So if I'm gonna have an AC input port, the first thing I gotta do is get it over to what? DC. This is called an optical isolator, optical coupler. And what we do, and this is a photo transistor, which is what this guy does. So what I've got up here is I've got this little remote for my TV, and I can flash lights, and that photo transistor picks that up. Right? You understand? I can drop this thing, and that don't hurt that sucker up there at all, because it's what? It's isolated. Where I'm bringing this input from the outside world, where we got all these idiots out there, and I'm going to bring that into my PLC, and I'm not going to protect that. How many PLCs do you think we would blow up because guys hooking up things backwards and stuff like that? So we isolate that. So this is exactly the same thing, except this is built inside a chip. You don't see this. So this would be like that little thing I've got on my hand right there. And this would be like the photo transistor that's up in that unit right there. Right? You understand? So now I've protected this is the PLC over here. TTL, by the way, is transistor logic. This guy runs off 5 volts. This guy is over here. What am I putting over here? I put 120 volts over here. So we come over here, we add resistance, so my input device don't have to provide a lot of current. We protect our Zener. We turn on lights, we flash lights with our input. This is transferred inside the PLC. I got an idiot that comes out here and puts 1,000 volts out there. It blows this optical coupler, but it don't blow my PLC. If I've got a spare input port, now what can I do? I can move it over. You'd have to redo your program. If I let that sucker come directly in and somebody screws up out there, they're going to blow my PLC. So every one of our inputs are isolated by what we call optical coupler. And it works just like that remote. It might not work. Because I did something stupid. Huh? Yes. No, I woke somebody up. You can't see these. I can bring some in. They're usually only got 6 pins on them because it don't take very much. This would be a typical DC inverter. And we'll talk about syncing and sourcing. But here we don't have to rectify it. All we got to do is, normally, this is probably an LED. What they normally do on your inputs is they put an indicator. And these guys are great. Because we tell our program to turn on, and when we're expecting an input, what we've got on this thing is we got a light that indicates that the input's true. So used to, if I didn't have an input, I'd have to get my meter out and I have to find where we have the open at. Right here, I can look at the PLC. If it lights up, it means the input is okay, right? You understand? If it don't light up, then I'll go out in my circuit and try to figure out why. So we can do a lot of troubleshooting on a PLC just by looking at the lights on the front. So when it generates an output, it turns on an LED. When it sees an input, it turns on an LED. So every input port it has an LED on it that indicates we're getting ones and zeros in, right? So if it's a zero or a no voltage, then the LED will be what? Off. If it's on, it means it's seeing a voltage which represents a 1. So that's what's nice about binaries. We can easily represent binary with voltages, right? 0 volts would represent a binary what? 0. 24 volts would represent a 1. We do the same thing with, and this talks about the optical transceiver. This is kind of misleading. It's not even a transceiver. If you look up transceiver, what do you think transceivers mean? Transceiver. So the book is definitely wrong. Receiver means it can transmit, which means put it out or receive it. These guys are not transceivers, but they usually come in groups of 8s. So we'll have one chip that would handle 8 ports. So they call them optical. But the inputs would be optical receivers, and the outputs might be optical transmitters. But odds are we don't even see that anymore. Allen Bradley runs in groups of 16, and Siemens runs in groups of 8. We'll look at that. So they left off the protection too. And we won't have the rectifier bridge unless it's AC over here, right? By the way, the lab book, you'll see a lot of this 120 volt in the lab book. So this text that I have was basically written to coincide with the lab book. Undoubtedly, when the guy wrote the book, he was dealing with a PLC that used 120 volt input module. All our input modules were 24 volts DC. So it's talking about what I just. So the Zener diode is in there to set the voltage. Octal latch, we're not going to look at that. A triac, by the way, is a device. This is an output port. This would be an AC output port. So notice what we have. Here's our computer. Here's our output device. Here's our output device. And what do we couple it through? We couple it through an optical couple. And why? It protects the internal works of our PLC, right? If I screw up real bad, what might I lose? I might lose this. But if I've got a free port, what can I do? On this, guys, if I didn't protect that guy, I would probably blow up every one of these modules between here and there, right? You understand that? Going from my output to my input, if I let those big spikes and stuff get on my backplane, I could wipe out every module I have in my backplane. But all I might do is lose what? 1 bit on my what? On my output. We're only using 8. We got 16. We could easily move over, right? So hopefully y'all not going to screw my thing up. These are the actual true outputs that we have. We have a DC output which uses a transistor. We have an AC output which uses a device called a triac. It'll actually pass AC, which is pretty neat. Some people call them solid state relays. It works really good. Then we have what we call relay output. Now, what's nice about it, it's got a DC output. The only thing that it will control is DC. If it's got a triac output, the only thing it will do is control AC. If it's got a relay output, you decide what you want it to control. So you can hook it up to DC and switch DC, or you can switch it up to AC. You can put 24 volts, you can put 5 volts, you can put 120 volts out there. So the advantage of a relay output is that it doesn't define what type of voltage you're trying to switch. Now the disadvantage of relay outputs is they're not extremely fast. Because you got an electromechanical device that's got to do the switch, right? You understand that? Another thing, they're electromechanical, which means what? Yeah, you got 2 ways they can fail. They could fail what? Electrically, or they could fail mechanically. The 1100 there, it has relay outputs. This 1000 has relay outputs. This guy here has transistor outputs, and the Siemens has transistor outputs. So this guy here says it's DC inputs, relay outputs, and AC power. Now it's becoming very, very popular to do some neat stuff. Like to control a stepping motor, we want to put out a series of pulses. There's a lot of relay PLCs that can't do that because it's not that they don't support the instruction, it's just that the relays can't do what? Can't switch fast enough. Another way that we control a DC motor is something used pulse width modulation, and a lot of your relay output PLCs cannot do that because it just can't do what? It can't switch those. So there's some instruction, but it supports the instructions. So these are output ports. These are true output ports. The book only talks about what? AC outputs, right? But actually we got 3. We got a DC output, right? You understand that? We got a AC output, which uses triacs. So triac will not pass DC, but it'll do what? It'll pass AC. And then we got relay outputs. Relay outputs can either be AC or DC. Are we okay? A lot of stuff, right? Let's see what. How many we got. So if I live in an analog world, but my computer only understands binary, then we have to have the ability to convert between the two. I'll try to demonstrate this before the 1200, I've got a potentiometer hooked up to it, and I can show y'all what it does for analog. But a special circuit that converts analog to digital, we called it analog to digital converter. And then if I want to communicate with an analog world, then I need to go from one digital analog. That makes sense? We'll get into it a little more in more advanced classes, but the book talks about all this. So what we're going to do is we're going to deal with, of course, communication. First of all, we've got to make our computer communicate with the PLC. Okay? So we'll figure out how we do that. Then we can also, we don't have time in this class, but you can also let PLCs communicate with other PLCs, which really isn't it. What we'll do this semester is just figure out how to make our computer communicate with the PLC. This is an Allen Bradley PLC. This is a RS-232. They called it a RS-482, I think now. Which is this. We don't support this anymore. So we have a dongle which converts it from USB over. So both our 504 and our 1100, our 1000 fixed PLC uses the RS4, uses what they call the RS-484. The furthest we're going to get is through timing and counting. We're going to do logic. So we're going to develop outputs and inputs, right? We're going to have digital inputs. We're going to learn how to program ands, ors, nands, nors, nots, exclusive nors. We're going exclusive ors, exclusive nors. That's logic. And then we'll play around with. They say, okay, the way the book is written, or the lab book is written, it gives you an application, and then you figure out how to do it. Some of them is pretty easy, where it says, write a group of instructions that do this. It's pretty straightforward. And then later on, they're saying, okay, I want to do this. I want to start a motor 10 seconds, and I want to count, and all this other kind of stuff. And we'll end up with counters. I'll figure out what counters do. Count. Timers. We run into timers all the time. Washing machines, right? Ice makers. Most of your cars now have timers on them. Most of us now just leave our lights on all the time. Turn them off for us, right? Turn them on for us. When I get out of my car and leave my lights on, right? You understand? And after a certain amount of time, it does well. That's as far as it gets here. Later on, we'll get in, if you take the PLC2 class, we'll get into data manipulation, arithmetic. We'll get into advanced logic. We'll get into sequencers, data manipulation. This is really big. What can you do with the data besides output and input? We already know what a driver is, right? What's a driver? It's a little program that supports or controls a specific peripheral or port. We know what an instruction is. What is an instruction? It's what we put in a program to tell it what we want to do. So I don't know if I need it. Oh, no, I think I read it. So that right there, this right here is an instruction. 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 But instead of me trying to learn a bunch of opcodes, right, I represent instructions with symbols, right? You understand? That makes sense? So we're going to learn instructions, but ours are going to be graphical instructions. And like I said, machine language, we're okay there. This is binary language, microprocessor understands. So look at this. This is what we're dealing with right here, high level. Now every language above this language has to be translated. You understand that? So this is an example of, let's see, the only language the microprocessor understands, all languages above machine language has to be what? Translated. Binary, we talked about that, operational codes. By the way, one thing that the book uses often, something called an operand. So we got opcodes, or operational codes, and then we got operands. And the book don't talk much about opcodes, but it talks about operands all the time. Everybody know what an operand is? This is the numbers that the instruction operates on. So if I add two numbers together, then the two numbers that I add together are operands, right? And the answer would be what? An operand. Programmer must know it. So if I'm going to do it, if I want to do machine program, I got to know everything. I got to know the microprocessor registers. I got to know the capabilities. I got to understand the instructions. You're going to have to know what is syntax. It's not like the tax on cigarettes and stuff.
Syntax is the logic of how the program is written.
Well, sort of, but it's the written language. Syntax is the correct way of writing it. So when you take your English comp class, right, and you don't put a comma, that is not spelling, that is syntax, right? Spelling is syntax. So the correct way of writing in a language is syntax. When you take those things, all that stuff you learn about sentence structure, about which type of symbol you use and all that, you're learning how to use syntax, right? And most of the time when you take an English class, what do they grade? Or composition, they grade syntax. So syntax, and you got to know all the addresses, assignments in the computer for all your input, your memory, and input output devices. Very complicated. How could I understand the addresses on this machine right here? Unbelievable. This is a machine language program. Are those instructions or they're operands? Are those opcodes or operands? I have no idea. I'd have to know the sequence of the program and where they're saved. How many could write programs in this language? This is the language. The first time I learned, but it was only an 8-bit processor, so it could only have 255 instructions. So they didn't use all the code, so it wasn't too bad. And you use a chart. You could look up a chart. I already showed you all the instructions. Assembly language uses mnemonics, which is basically memory to represent instructions. This is translated into a machine language program by something referred to as an assembly. Even though it's still complex, it's easier than machine language. The programmer must still know the registers, the instruction syntax, the IO addresses. So this was the next step up, and some people still use this. So this is assembly language. So move into the AX register the contents of address 01020 hex, which I don't know hex. But this is assembly language. But now it's moving more toward English, right? It's still very complex, but you still have to know all the registers, and you still have to know all the addresses, but I don't have to know operational code. All I gotta do is know the mnemonics represent. So we don't do this much anymore. Then we get into high-level languages. Written using terms and expression common to the English language. I should put terms and expression in symbols. Does not require knowledge of the microprocessor or addresses translated by an interpreter or a compiler. Some high-level programming languages, we're going to use ladder diagram. Then we have structured text, we have function block, and we have sequence and flowchart. And all those are written toward people coming up through different disciplines, right? So if somebody has been writing programs down in computer science, they would have no idea about motor control or ladder. So they would want what? Structured text programming. People who come up through truly electronics and didn't have anything motor controls, they would like to know function block programming because they use symbols. People that came up through computers and dealt with flow charts. I don't know if y'all remember flow charts. That's what sequential flowchart programming is. It's very similar to that. So you just draw flowchart symbols, and then your translator will translate it over to machine learning code. This is the one we're going to learn. And why? Probably over 90% of the programs written for computers use structured text. And I don't know of anything you can do without it. This is a basic. This is the old basic. CLS means drill string. Input means I want to get stuff on the keyboard. How old are you today? That would pop up on the screen. I put it into a variable called age. Then I say my days is equal to the age times 365 plus 365. Friend, it says you will be D. It could be whatever the answer to this was. It's going to pop that in there for me. Days old on your next birthday. This is a language called BASIC. Very similar. If you did Visual Basic, which is a proper programming language for writing applications for Windows. It's basically this, but you have graphical stuff you can play. This was the first high-level language I learned. And I said, man, gosh, this is so easy. Yeah, all you do is learn it, man. All you got to do is get the right syntax. If you misspelled input, then odds are when you try to translate it, it would come up and say you got a syntax error. Ours don't say syntax, I don't think. So there's the basic language. We're going to use what language? Ladder. And guys, there's only, so we got a normally open contact, a normally closed contact. We got a latching contact. We got an unlatch. And then we got timers and counters. So those are the only symbols that we'll have to understand. I think that's all we're going to do here. So now what we do is we program with a PLC. We run an application on our PLC, right? Understand? And that's what we'll try to get into. What we're going to start into Monday is we're going to start into the chapter on numbering system. I talked to Miss Wilson. This used to be her class. She taught that first. So what chapter is numbering system? 3. Also, the first lab that we're going to do is going to be a homework lab, and it's going to be convert numbering system. So you need your lab book. Everybody okay? We're going to go over it Monday, so we'll probably turn it in. Are we okay? Questions? Did y'all learn something tonight? A lot about computers that you didn't know. Now you're very impressed about the people that design and write the program.
Just random things I know bits.
Oh, yeah. I'm actually, I wrote a book that was published about
Everybody just the syntax of AG robots is what I learned.
Syllabus, we don't have the syllabus, we have a syllabus brief. The syllabus is on Blackboard.
Yeah, I need, do we, need to do anything, are there? Do you have any Blackboard assignments or anything?
Yeah. It's on the brief and
That needs to be done by Friday, right? By the end of the first week. I mean, I can just look at it, you got three
The brief is
on
on-
Blackboard,
yeah, it's on
that's
Blackboard.
fine. I'll just do it for that.
these are all.
And I know, I've learned a whole bunch of different syntax for, the A and B robots. Is what so I was trying to think like how to code, like if I were to do I guess the programming on the computer, but most of the programming on there, all you gotta do is click a thing and then put it.
That's the same thing you do here. Yeah, you select an instruction.
Yeah.
Well, that's not true. A lot of the stuff on simulation, you got to type it. It's got all your move instructions. It does not have any of your output or input instructions. So yeah, on that simulator, I don't know, that's the only one we got is the one for both.
What's funny is a lot of binary, I know a lot of, I knew already did with the stuff with binary, and you know who taught me? Was my Uncle Mike, who you taught.
Oh, really?
Latham.
Oh, Mike Latham?
Yeah. He's the one who taught me that, so he was like, yeah, that's what we used to do, that's all we did, and I was like, oh, okay.
When did he come through the program?
He took some classes, I don't know exactly.
He did graduate though, didn't
It was like 35 years.
he? Yeah, but don't make a difference. I've been here since 82. No, he was here before then. 'Cause I've been here 37 years.
Well,
And I don't think he was that close